All right, I want to revisit a couple of things with Kmaps. So let's take a look first at our outputs. And we're going to take each of these last 6 columns and we're going to make them into a circuit by going through a Kmap. When we make a Kmap, we should have, when we circle our ones in our largest blocks, we should end up with the simplest circuit just by circling the largest possible blocks, as long as they're in a group that is a 2 to the nth multiple. That is 1, 2, 4, 8, 16. There is one outcome where that's not the case, and that's here with dB. So let's Kmap that one and take a look at why this is not the case. So it looks like we have ones at binary for 2, so binary for 1 and 2, and again for binary 5 and 6. So let's transfer that over to our Kmap. So here we're going to find the output for dB, and I'm just going to make a little notation in here. 0, 1, 2, 3, 6, 7, 4, 5. And remember, we had ones in 1 and 2, and then 5 and 6, and we had zeros in the other scenarios. So if we were to circle those up, I could circle these two, and I could circle these two in a group. That would leave me with QB enable not plus QB not enable. That looks like the simplest circuit, but it also looks like I could almost simplify that in some way, applying some Boolean algebra, but the truth is that's not going to get any simpler with some Booleans, not the ones that we know in our class at least. So let's take a look at this and see how we could simplify that. To do that, I'm going to take a look at a single circuit. So let's examine our XOR output. So our XOR, we have X, Y, and let's say Z is our output. Let's put a double line there. If we have 0, 0, we're going to have a 0. If we have 0, 1, we'll have a 1. 1, 0, we'll have a 1. And if we have 1, 1, this is what makes it an exclusive OR, we'll have a 0. So what's happening here is only when Y and not X is true will we have an output of 1, and only when X is true and not Y is true, and not Y, will we have an output. And the truth is, we have that right here. Well, if I literally say this, it's Q is true and enable is not, or when enable is true and Q is not. That makes sense. That's an exclusive OR. And the way that we write that is, we write it QB plus EN, like that. So we can simplify that down. If I was to write out, let's change back to purple. If I was to write out this expression here, I would probably need QB, and if I was to convert this into a circuit, I'm going to end up with a bunch of things. I'm going to have an inverter, I'm going to have an AND, I'm going to have an OR, I'm going to need the same thing this way. I'm going to have an inverter, I'm going to have an AND, I'm going to go into that OR. And so I have 1, 2, 3, 4, 5 gates required in order to make this circuit. Or I could just take and have it be something like this. And you are going to functionally have the exact same output. So that's the power of the exclusive OR, and that's why we would like to use it in our circuit here.